We'll be talking about Quasimap wall crossing applications and generalizations. So let's welcome him.
All right. Thanks very much for the introduction. It's my great pleasure to speak here. Today I'm going to talk about some Quasimap wall crossings, and the plan is as follows. So first I'm going to talk about a very classical problem, counting curves on Queen's threefold. Of course, this has been well studied for a long time, but I'm going to look at this as a motivating example from the point of view of Quasimap wall crossing. And actually, only from this example, we can see basically all the ideas of epsilon stable Quasimaps, the notion of epsilon stable Quasimaps, the wall crossing formula, and its proof. So the notion of the theory of epsilon stable Quasimaps works for more like target spaces for a wide class of GIT quotients. But the stability condition, the form wall crossing formula as it proved, they are basically the same. They are not sensitive to the target space. You can just carry this proof constructions over to any GIT quotient verbatim. And then I'm going to talk about more examples and some applications and generalization. Okay, to start with, let's fix some notation. So let X be the quintic threefold. Okay, so this is the Calabi-Yau threefold. So by this dimension counting, one expects that there are only, at least expects that there are only finitely many curves in X for each genus G and degree D. So G will always be the genus and D will always be the degree. And let's say this is defined by some polynomial where f is this defining equation for X. Okay. So for example, the first number, so if we look at GN0 in curves, then the first number is just the number of lines in X. And this is can be calculated by the Schubert calculus. And if you go to degree 2, then you are counting the number of conics in X. So we assume X is general, otherwise we don't always get a finite number. We assume X is general. Then this is like hundreds of millions, hundreds of thousands. Okay. So and the next number is too big. I can't remember. It grows very fast, and it's not easy to compute, and it's even not trivial to define these numbers because you only expect there are only finitely many curves, but that's probably not true in general. So when the degree goes higher and higher, it's much better to count maps instead of embedded curves. So then we come to the Grombillion invariance. So this counts maps into X. So this and introduce some notation as MG XD. That's the moduli of maps from C to X, where this X1 and Xn, they are markings on X. So where this C is a nodal curve nodal n-pointed curve of genus G. And F is a map of degree D, so the degree of F, well, it's just the first chain class of the pullback of O1. We fix a polarization here, for example, coming from the hyperplane class on this P4. That's equal to fixed to be D. We fix some discrete topological notation, like data. And most crucially, that we require that the automorphism of the whole data is finite. So this is a modular stable maps by Quasimap. So it's a proper space. Actually it's a proper DM stack. So if you don't work with stack, you can just think of just a proper compact hostile space. In general, it will be very singular and not of the expected dimension. We counted naively, but from the naive count. So to resolve these issues by the work of Li Tian and Baron Fantacchi, so they using deformation abstraction theory on this space, they constructed some so-called virtual cycles. This is just some homology class in the modular space. It has the correct dimension, and it is the one you should get when the moduli is nice. And so this homophonetic invariance can be defined by intersection theory against this virtual cycle. So, for example, if this GD can be defined as we use this integration notation. Just integrate 1, just by definition, it just means the degree of this homology class. Sorry, this is, if there's no marking, then it's a degree 0 class for Calabi threefolds. But more generally, if we have more mark points, then we can count curves intersecting some fixed locus in the target manifold by requiring the mark point to go into that locus. So topologically, that means we fix homology classes on the target manifold X. Then we use a bracket notation, so gamma 1 and psi to the A1 up to gamma n psi to the AN, Gn dx. That's defined to be, we still integrate against this virtual fundamental class, but we integrate the pullback of the cohomology classes via some evaluation maps. Okay, where this evaluation maps are from the moduli to the target space by sending the datum of the point to the evaluation of the map at the ith mark point. And the size are just cohomology classes on the modular space, which is defined as the first chain class of the line bundle Li, where Li at this point in the moduli space is just a cotangent space to the curve at the mark point. So when you have these psi classes, it just you can think of those as counting curves with not only incidency relations but also like tangency conditions. All right. Basically, I'm reviewing this to set up the notation for later use. All right. So now before we have this little ngd, which counts the actual curves inside the Calabi-Yau manifold. But here, the capital ngd are counting maps. They're related, but in a very like not obvious way. So, for example, for lines, they are just the same, and but for conics, we have the contribution from the embedded conics plus some contribution from the double covers. We're counting degree 2 maps. The degree 2 map can be like a degree 2 cover, 2 shaded cover of a line embedded in the quintic, but with a mysterious factor here. Okay. So anyway, in today's talk, we're going to be focused on counting maps because that's easy and well defined for any target space. All right, so the GS0 like curve counting on this Calabi-Yau threefold x is still the quintic. So that is solved by the mirror theorem in the 90s by Giventon and Lianliu Yao. There are different ways of stating the theorem. Today, let me state it this way. So first, we write down some mysterious. Okay, so maybe it's not mysterious from physics. Mysterious if we only look at this mathematical counting problem. So the I function, sometimes also called the vertex function from representation theory. Well, it's IQZ. It's a formal series with 2 parameters, a summation for all degree D, and it looks like a hypergeometric series. Okay, it takes some time to write down. And times q to the d. So it's a very complicated series. You can, because H is a hyperplane class. In this H2 of X, in the target space. So H is nilpotent, so you can basically, this is nilpotent, so you can expand the function when you invert this Z variable. So if you do that, it actually lies in this thing. So Z plus minus 1 and Q. Some very complicated expression. And the upshot is that the theorem is that, well, roughly speaking, we don't need a precise like statement in this talk. So we are just roughly speaking that this I function, it determines all this N0D for all D. Okay, there's a like explicit way of doing that. Okay, so next I'm going to explain why this function and how that's related to this confiniment. We'll see that there's a geometric way to see why you have these factors that contribute to this number. Sorry? definition of the coefficients. It's very complicated. So you basically you write this as like expand it as 0 plus I1 h over z. You expand it. Then you have to multiply this by some factor, and then you have to do a change of variable, like capital Q is equal to and this capital Q will be the variable that keep track of the degree d here. It's still a non-trivial relation, but I'm going to explain why we see this function from wall crossing. Oh, sorry. It's related. So basically, you do this kind of manipulation to the I function, you get a J after the change of variable. Okay, that's a theorem. It takes some work. You need to do some computation, but not once you have the wall crossing, it still takes some computation, but not very hard. Okay. Okay. So let's first analyze the problem. So I think the main difficulties, at least from the geometric point of view, is that the domain. So we're looking at the G0 unpointed like stable maps of degree d. Right? We're looking at this space. So one of the difficulty that domain is irreducible in general. I mean, domain may be irreducible. So the domain might be very complicated tree of rational curves like this. The domain might be like this. So this is a domain. That's one of the difficulties. The other difficulty that even if the domain is reducible, you want to look at that kind of maps, the domain is not parametrized. When the domain is irreducible, it's isomorphic to P1, but not canonically identified with P1. It's not parametrized. You need to somehow quotient out the automorphism of the domain in order to count actually curves. Okay. So now let's just forget about these difficulties and do this counting in the most naive way. So how do you write down a map? So how do you write down a map from P1? Let's just fix domain to be the parameterized P1. So how do you write down a map from P1 to this X sitting inside P4? It's given by just some homogeneous polynomials, 5 homogeneous polynomials, right? And when you plug in the polynomials, plug the polynomial into the defining equation for X, you have to output the 0 polynomial. That's how you write down a map to X. Of course, they have to have no common zeros in order for the map to be well defined. Okay. So because of that condition, the moduli of maps from a parameterized P1 into X is not compact because they might develop some common zeros. But let's just ignore that. So just define the Quasimaps from the parameterized P1 to X of degree D. That's defined to be just F0, F4, where this Fi, they are like polynomials of degree D, homogeneous of degree D, polynomials, and they are not simultaneously the 0 polynomial. That's only requirement. They are not simultaneously like identically 0 functions. And of course, I need to impose a condition that they satisfy the defining equation for the hypersurface. Okay. And then we mod out the C star action. That's a common scaling of all these 5 polynomials. So without this additional condition that they satisfy the defining equation of the hypersurface, without this condition, that's just a huge project space. Just recall the coefficients of this polynomial. But now you have some additional defining equation which makes some space actually singular. But anyway, now let's look at the difficulty 2. Difficulty 2. So we need to somehow kill some automorphisms of the domain. Let's just look at the maximal torus of the automorphism of P1. Just consider only the C star action on this one. This is by scaling this P1. I have fixed some standard like scaling fixing 0 and infinity on P1. So by composition, it scales all the polynomials. And so we have this C star action on this Quasimap space. And among the fixed loci, there is one distinguished fixed loci. There's one fixed component, fixed point component. We denoted it by F star. It's the only one we will care about. So, of course, for a fixed loci, the map has to be like a constant map. Okay. So here we don't allow, we do allow them they have like common zeros. So they do not define a map on the whole P1. They define a map almost everywhere on the P1 because the zeros are discrete. Right? So, but anyway, the rational map has to be a constant map. And we actually only looking at this, the most like trivial, non-interesting case, where the polynomials are just multiples of u to the d, where this uv are the coordinates on this P1. And this time we require that this A0, A4, they have to be numbers that are not simultaneously 0. So that's actually, and satisfying the equation for the hypersurface. So they are nothing but just a point in X. Okay. So this is a Quasimap. This is inside this space. And okay, then how is this related to the mirror theorem? So this basically only parameterizes constant Quasimaps, but the space is not interesting. It's just the only data is just the 5 numbers representing a point in X. So this is nothing but just isomorphic to X. It's not very interesting. But the I function we have defined before, if we take the Q to the D term, it turned out to be just equal to 1 over the Euler class of the normal bundle. Okay, I'll explain. So here we put virtual here because the ambient space is actually not smooth. But we can write down like this sits into a big Pn by removing this condition. And we can write down the defining equation for this one inside this Pn, basically coming from this equation. So it's somehow like a nicer complete intersection. So we can have this tangent is like a 2-term complex. So we can so we can have this take the quotient of the Euler classes. And this is a fixed part, so its normal bundle has a sister action. We take the equivariant Euler class. So this, by definition, sits in the H star x, where z and z minus. So here, before z was just a formal variable, but now z is a equivariant parameter. Okay, that just means that it's if you look at the equivariant cohomology of a point, that's z is the generator. So it doesn't have, now it has a geometric meaning. So the upshot is that, or the slogan that, so counting this constant Quasimaps. So because this one parameterizes constant Quasimaps, so they determine counting stable maps. Via this Quasimap wall crossing. Or maybe it's time I have. Yeah, question? Oh, no. Okay. So it has perfect event theory. Yes. Yeah, so this one basically is just and so the numerators come from the deformation of the polynomials f0 to f4, and the numerator come from the condition that they have to satisfy the defining equation for the hypersurface. Well, in order to explain this, I need to explain the definition of Quasimaps. So a pre-stable Quasimap C. Let me write dot 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 because it's not actually a map. So X is still the quintus threefold. It consists of the following datum. So C and X is just a collection of all markings, and a line bundle plus together with sections. Okay, so here a map from P1 is just given by homogeneous polynomial, which is the section of the OD on P1. So here now we have an arbitrary line bundle where this first, this Cx is just a pointed nodal curve. And second, L is a line bundle of degree D on C. And phi 0 to phi 4, they are sections of the line bundle. So they define a map to P4 if they do not have common zeros, satisfying the equation of the hypersurface. Okay, pretty similar to the previous story. And then the next requirement is that I need to, okay, so such that the crucial notion that if we look at the points where they do not, where the map is not defined, that is the locus where all the sections vanish. So this is called the base points. So the requirement that this is finite and disjoint from nodes and markings. Okay, so it's almost a map, except for some like general points containing a smooth locus, not special points. The nodes and markings are special; they cannot be base points. Otherwise, it can be there can be finitely many base points. So let's denote the moduli by just Quasimap from genus G and unpointed to X of degree D. And by definition, the moduli of stable maps is like a subspace of this small space, and it's actually an open subspace. So this is proper, but it's open in this thing. So this is it's not surprising because this is a very huge arcing stack, non-separated. It's too large. So in order to single out like subspaces that we can work out invariance, we need to put stability conditions like this one. We put a stable map condition, we single out this one. Other stability condition will give us different open substacks which define different invariants. So now actually there's a family of stability conditions defined by Kilcan-Fontaine and Kim and Malik. So it's called epsilon stability, where this epsilon is the parameter. So epsilon is given the fixed positive rational number. So given this number, a Quasimap C, X, L, and phi is the collection of all the sections, is epsilon stable. Is the following condition satisfied? First, so for any base point, base point is just a common vanishing of all the sections. The common vanishing order cannot be too big. So the condition that denoted by, we call it the length of the base point, which is defined to be the minimum like of all the vanishing orders of all the phi I at this point X, where we go through all the sections. So this has to be not too big. And the second is that there is some positivity condition that L should be sufficiently positive. This is positive. Positive means that it's ample. It's equivalent to that on every irreducible component has strictly positive degree. So here epsilon is a rational number, but this is a Q line bundle, but positivity makes sense, right? And where this omega C log is defined to be the omega C twisted by the divisors. This is a log dualizing sheaf. All right, basically okay, that's a epsilon stability. So basically we have some control on the so the first one is clear, it controls the order of base points. The second one actually controls the bubbling of the rational spheres. So for simplicity, let's introduce a jargon, which let's call this, okay, so this kind of a component where this point is either a marking or a node. Whenever we have such a component in the domain curve, we call this a rational tail. Okay. On the rational tail, this bundle has degree -1 on this rational tail. So the condition just translates simply into that. So for rational tail, the stability condition 2 for this C prime is just equivalent to that. The degree of L restricted to C prime is at least 1 over epsilon. Okay, now this looks similar to this one, right? So they are like competing with each other. And similarly, if we have 2 special points on a Riemann sphere, we have 2 such either marking or node, then this one has degree. The requirement 2 is that this is positive. But we see that this is independent of epsilon. So in this talk, we'll mainly focus on rational tails. So all the story is about rational tails. So maybe let me just copy the stability condition here because that's very important. Other things. So epsilon stable just means that the length of base point is most 1 over epsilon, and the degree of this so base point, the degree of the rational tail, plus other things, but other things are independent of epsilon, so I'm omitting them. So, okay. Oh, by the way, so QCAM14 Kim-Malik they prove that the modular of epsilon stable quasimaps is again proper, so they have epsilon stable quasimap invariants. So we have different invariants for every epsilon, and there's the wall and chamber structure. Coming from the fact that the length of base points and degree, they are all integers. So it only jumps when this is 1 over some integer, when the right hand side is some integer. So we can draw some picture like this. So this is epsilon, and here for example, this has degree 1, we have degree 2. So when epsilon is big enough, then this is stable maps, and it gives the Gromov-Freitag invariance. The reason that when epsilon is big, then this is base point is can only be 0, so there's no base point. And this one just becomes that the degree is positive, which coincides with the stable map condition. So these are degrees, and but if you cross the wall at epsilon equals 1, then you disallow this degree 1 rational tail because this condition. So you have to contract this rational tail to here, and this is a base point, creating a base point. So now the degree moves to this component. It has degree 2 now. This degree 2 is unchanged. So these are the rational. Sorry. So these are Riemann spheres. This is some hygiene component. And if you cross the wall again, the next wall, then you have to contract all this degree 2 tails, because degree 2 tails are not allowed anymore. You produce some base points of a higher length. You see that there's a wall and the chamber structure. And this is most useful when GS equals 1 and n equals 1. In that case, the domain is just a tree. It's just a tree. There's a root. The root is just coming from the marking. It's a tree. And after all these wall crossings, when epsilon goes to not to 0, but to 1 over degree, there's a last wall. After that is unstable. So to some limit, the domain has to be just some irreducible P1. You contract all the tails until the domain becomes irreducible P1 after this wall crossing. So roughly speaking, the wall crossing formula relates invariance in different chambers, and it tells you the contribution of the rational tails to the convolution invariance. And when in this case, the whole thing is only a rational tail, so you can use it to compute everything. That's like a geometric reasoning. Sorry? Sorry. Yeah. Yes. Invariance for classes, both. From classes, you can get invariance. So the wall crossing formula looks like this. That we similar to the GW invariance, we have the Quasimap invariance, and we compare the invariance in two adjacent chambers. So here we have like a wall here, which is epsilon 0, which is 1 over d0. You have epsilon plus and epsilon minus. We have two stability conditions in adjacent chambers, and okay, then this is equal to like k 1 over k factorial, and such that mu to the d0. You plug in psi here. Okay, there are k additional insertions. Okay, I'm not going into more details, but just this is just a power series. This just some truncation of the z function, the q to the d0 term. Okay. So you just throw away the z negative parts, and okay. So it looks complicated, but geometrically, this just represents the contribution from this kind of locus, where you have like k degree d0 rational tails. You take them away, that's the remaining part. But you create new markings coming from the nodes connecting to the tails, and then insert some truncation of the I function coming from this. And all right. So maybe I'm short of time, so let's just me roughly explain the idea of proof. This is a work by myself in 2022. Okay, so it uses a so-called master space technique. So the idea is we merge two stability conditions on different chambers, which means we allow, like, for example, if we cross this wall, we simultaneously allow degree D0 tail and less D0 base points, which is kind of a union of the two sides. But what we get is that some objects will have like infinitely many automorphisms, which are things like this. So this has degree D0, and this one has length D base point. So this kind of things are the most troubling because they have like infinitely many automorphisms. From the localization point of view, those should be the one that contributes that actually contributes. And you can see that from this picture, if you only look at this part, looking at this part, this is precisely what we used to define the I function before. Right, then let me explain. So Quasimaps for GIT quotients. So the target space, it cannot be like arbitrary, like abstract manifold. It has to be coming from a GIT quotient, where that we assume that W is a phi and G is reductive. It doesn't have to be abelian, but it has to be reductive. And theta is just a character of G. So this is a new X now. And then W, it has to have no strictly semi-stable locus. And this has to be smooth. And the whole W has at worst, the unstable locus can be singular, but at worst LCI singularity. Those are some technical conditions. So for example, the previous quintic, it can be realized as a GIT quotient by C star. And what is this? This is the affine cone of X. It's just a vanishing locus of F inside this C5. And so this is the only unstable point. So now, in order to generalize the story, we need to generalize three notions. So first is the Quasimap. The Quasimap now is just a map. There's a fancy way of writing this. It's just a map to the Artin-Stein quotient. But in concrete way, it's just equivalent to that. You have a principal G bundle over this P together with a section of the associated W bundle. And we need to generalize the notion of base points. This is also the work of K.F. K. Molik. So base points are just the points such that the sigma is sent to the unstable locus. The unstable locus. So for example, in this case, the unstable locus is a cone point. So that's where all the 5 sections vanish. And the degree, there was a line bundle L, but we just replaced the previous L by, there's a canonical line bundle coming from this GIT quotient, which is just induced by the representation theta, the character theta. Replace it, so we have a well-defined notion of degree. So and everything just generalized to the GIT quotient case verbatim. Okay, now there are many examples, more interesting examples. So first, it doesn't have to be just a project space. It can be, in general, toric varieties. And also toric complete intersections. In the non-abelian case, you can just consider the Nakajima quiver varieties. Instead of toric varieties. And okay, and the convenient sections. Okay, those already give you many interesting examples. Let me talk about some more concrete examples and applications. So let's look at the seemingly trivial case where X is a point. The GIT quotient is a point, but the Quasimap theory can be non-trivial if we write it as a quotient like this. So recall that a map from C to this one is just equivalent to a line bundle plus a section. And the section is required to have only discrete zeros. So it's basically a Cartier divisor on this X, continuous smooth part. So if we don't allow zeros, then the line bundle has to be trivial, so the theory is trivial. But now we allow some finite zeros, finite many zeros, so it's less trivial. So we do this, we repeat this many times, so we have well, in particular, if L is of degree 1, if L is of degree 1, then it's just a point, a marked point. And so this produces the Hesses moduli of weighted pointed curves. And the wall crossing give you like comparison between those spaces. All right, so second is that if you consider X7 inside P11113, so this is a Calabi-Yau 3, but orbifold. So because 3 doesn't divide 7, it cannot avoid the singular point here. So as the orbifold is like this, so there is a point B Z mod 3. Otherwise, it's just a smooth scheme. So, such a thing. So the Chen-Ran cohomology, the degree 2 part of the cohomology, you should consider Chen-Ran cohomology, is coming from there's a hyperplane class here, but there's also some contribution from the twisted sector. So you need like two different, the GW invariance is a Jernigan series should be with two variables because the Killer moduli should be thought of as two-dimensional. So corresponding to that, we should write this as a GIT quotient by a two-dimensional group. So we write basically 1113 not as a C5 mod C star, but C5 times C modulo C star times C star. It's similar to this one. So the GIT quotient doesn't change. But the Quasimap theory changes. So the weights, it turned out to be, if we use this weights, then the GIT quotient is still the same thing, and the Quasimap wall crossing can be used to recover all the determinants all before. Okay, so this is the work of and Navas and myself. Okay. Okay. Maybe last 2 minutes I can talk about some. Also, there's some. So in GS1, there's X is a funnel hypersurface. So you see that when the GS is high, then the wall crossing only get rid of the rational tails, simplify the moduli a little bit. So, but it helps in this case when the GS is low. So it can be used to compute some invariance and prove part of the GS1 Virasoro constraints. This is work in progress with Shuai Guo and Qingsheng Zhang and myself. Okay, maybe no time to talk about too many generalizations. So let me just mention that there's the K-theory version of generalization, which might be interesting to some people, and also there's Nesterov's work. So he gave a talk on Monday or Tuesday, beyond this GIT setting. So including like modular sheaves and like Hurwitz covers. Whenever you have this bubbling sphere phenomenon, the master field construction can be used to prove similar wall crossing formulas. Okay, I'll stop here. I think time is up. Okay, I'll stop here. Thank you.
Are there any questions?
Sorry, could you say something more about the K-theory version of you said generalization, right?
Yeah. There's like K-theory Gromfitting invariance.
Oh, okay. Yeah. Okay.
So
So does that mean you will get? Does that mean you will get quantum K theory? Quantum K,
quantum K invariance.
I see.
But it's not clear to us what can you get from the wall crossing yet. It's more complicated because you have like bubbling of several rational tails. You need to consider the permutation equivalent theory from those tails. Oh, okay. It's a little bit more complicated.
Okay, thanks.
Any more questions? If not, then let's thank the speaker.
All right, thank you.